Welcome to the second part of the Matrix Wrangler video. So we finished last time with reading in the data, assigning samples and compounds to internal standards and blah, 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 all of that. So now we want to sort of move on to the pre-processing stages. The next and very important step is normalization. I realized relatively late in the day that without normalization, most of the following analysis is not useless, but is skewed in quite a strong way. We'll see in a moment why that is. So normalization has to happen. Most of the time we don't know how to do it, but we've got here untargeted. We've got two things for free that might be quite useful for normalization, and these two things are the MIC and the tick. So the MIC is the median rather than the tick is the sum over all intensities per sample. If we look at this here, the MIC and the tick, we see that our first 5 samples, which were the pool, are quite a lot lower than the rest. Then we go up, and then there's some kind of, one could say, a drift downwards as the experiment carries on. I don't know for sure whether this is the order of the experiment, but it looks very much like it is. So here we can also, here it shows whether it's a sample type, whether the pool, also blanks. Blanks would also get a different color here. If we don't like that, we can also have we could color by something else, age, say. This is more sort of a cosmetic thing that will tell you a little bit which samples you're dealing with. And so if you hover over here, you see which sample it is, and if you click on it, you can see at the bottom everything that's known about this sample. Yeah, so if you like sort of playing around with this, plot a little bit, and then decide what you want to use for normalization, so either the MIC or the tick or one of these compounds here that let's presume that these are actually internal standards. So the top one here would not be very useful because here, in fact, these values look like there's something wrong with the graph. These are missing values, or in this case 0 values, and the scale is log. But anyway, can't divide by 0, so this compound here would in fact be out. We can't use it for normalization. Whereas this one we could. But probably we wouldn't want to use it because here there seems to be a lot more noise in it. It's anyway not an internal standard, so we shouldn't use it. So we choose something here. We see that the first sample, feature 0004, has already been removed because of the NAs. You can also say, I don't want to normalize. And then you press normalize. So if you don't want to, you have to press normalize, otherwise you can't continue with the analysis. Even if you don't want to normalize, you'd say no thank you and normalize. In this case, we'd rather normalize because it's really quite important. Or let's say, okay, no thank you. Let's see, we are a skeptic. We don't want to normalize. And here we go. So actually nothing has happened, but we are allowed to proceed to the next stage. And so here is where it becomes evident whether our normalization was successful. We want to calculate correlations between features. This is something that will be important later for identifying isotopes and neutral losses and what have you. To calculate the correlations, we need to set a few parameters: what kind of correlation, how we want to impute missing values. So this includes 0 values. I always impute 0 values, and I would usually use the min. Binner, for example, uses the median. Each to his own. You can log transform or not, and then you can say I don't want to. I certainly don't want to have the blanks. The blanks would certainly be a bad idea to calculate calculations. The pools might be all right. In this case, we will exclude both the pools and the blanks. And as I press preprocess, what happens? I get a histogram, and this histogram is a histogram of correlations. I've taken some precaution that the computer won't crash, so I'm only calculating it between 500 randomly chosen features, not between all of them. If you've got 10,000 in there, that won't make any difference. You will still only calculate sort of the correlation matrix for 500 randomly chosen features. Different ones every time. Yeah, but I guess let's press it again and see what happens. It does make a big difference. In fact, it doesn't make any difference at all. Huh? So now then, so what's the problem here? We see that in fact these correlations are very strongly biased somewhere very, very high, of 0.67. It's this is not right. Why are all these features correlated? Of course, there will be some features that really should be correlated and are correlated. For example, C13 isotopes, and so on. But most of them aren't and shouldn't. The reason why they show a high correlation here is because we haven't normalized. And it's simply that the correlation just follows the pattern of how much concentration in total there is per sample. And that's the same for every feature. And that's why so many features seem similar to each other. So if we don't want that, we have to take one step back. We say, Uzbek, okay, we don't see actually anything here happening. Then if we take a correlation, hopefully something's going to happen. And here we are. Now, if we did this, so now we have a profile that is much more to my liking, because it is centered on 0. This is what I think a reasonable null hypothesis is that on average, any two features will be correlated with a correlation coefficient of 0. Some of them will be negatively correlated, and some of them will be positively correlated, and it's roughly symmetric, and with a stronger positive tail. So, so within here, a small proportion of these will be real positive correlations, but we'll also get loads of positive correlations just by chance. Yeah, and that's but at least this plot here gives us a way to evaluate how our normalization has worked. We can also use other methods of normalization. This is a very good way of doing it. And once we've done this, we can now start looking at the features, which will be the next step, where we look at duplicates, isotopes, and neutral losses. This will be described in the third video.